Hello everyone, I'm Yulu Yi. It's a pleasure for me to give this talk at the FC2022 conference. The content of this paper I want to talk about is the efficient approximate calculation and application of network centrality. What we do in this article is to propose two approximate measures of closeness centrality. Then, we designed a parallel algorithm based on pregel to compute the proposed centrality. At last, in the experiments, we evaluate the effectiveness of approximate metrics and apply it by studying the relationship between executives' social ties and their firm's market value through a financial social network analysis on the Bordex. So, this page will tell you what is network centrality and what it can do. Network centrality is used to measure the importance of vertices in the network. Typical network centrality includes degree centrality, closeness centrality, stress centrality, betweenus centrality, which provide various options to describe the importance of vertices. And when we need to analyze the inherent information of features and connections in social networks, we often abstract social networks as networks in graph theory for computation. In particular, for example, we can apply this method to a financial social network to analyze the impact of the relationship between employees on the company's financial situation, so it can help the company's decision-making and management. Next, I'm going to talk about the definitions of two network centralities, closeness centrality, and harmonic centrality. Well, in a connected graph, the closeness centrality of a vertex is defined as the inverse of the sum of the distances from other vertices. And the formula is as follows. Where the d, j, I, is the length of the shortest path from vertex j to vertex I. In particular, for comparison across multiple networks, the average length of the shortest paths from other vertices is used here instead of the sum of the lengths. So its formula becomes as follows, where n is the number of vertices in the network. Using the idea of harmonic mean instead of arithmetic mean in the definition of centrality, Richmond and others proposed harmonic centrality, which is applicable to the computation of centrality in disconnected networks. And the formula is as follows. Where the lowercase n is the number of vertices in the connected component to which I belongs, the capital N is the number of vertices in the network. And the ratio of lowercase n-1 to uppercase n-1 is the harmonic factor. Then, we propose two novel centralities on the basis of previous work. First one, the k-closeness centrality. It adds a threshold k on the shortest path length to closeness centrality, and the length of the shortest path greater than k is considered to be k plus 1. So the formula is as follows. Where the n_k, I, is the number of the vertices whose distances from vertex I are larger than k. Second, the k-harmonic centrality. By the same token, it adds a length limit k on the shortest path to harmonic centrality. And they are considered connected if the shortest path length between two vertices is less than k. So the formula is like follows. It is the product of two formulas. Where the n_k, I, is the number of the vertices whose distances from vertex I are larger than k. And the first expression represents the harmonic factor on vertex I. However, computing the centrality of social networks consumes a lot of computing resources. So we propose a distributed parallel computing framework based on pregel. Pregel is a framework for processing and modeling algorithms on large graphs. It is a distributed programming framework from Google. It consists of multiple supersteps. And each superstep has three phases, like merging message, running vertex program and sending message. There is a barrier between each stage. The next phase starts only after all vertices complete the current phase and the sync phase. So, in order to use pregel, we need to define the above three processes. These is the designed algorithms for our calculation of centrality. We have defined the above three processes of pregel from 5 to 17. Where lines 13 to 17 describe the stages of vertex processing. We add 1 to all values d in the merged message, then add the key value pairs of the merged message to the map_v. Since during the send message phase, only the vertices that are not in map_v are sent, there will not be any duplicate keys in this step. At last, in lines 18 to 22, we compute the closeness-like centralities. After iteration ended, flatten map_v on all vertices into triplets: current vertex, source vertex, distance, and then, all triplets are grouped by the second element, i.e., the source vertex, where all these source vertices are from v_s, and finally, the algorithm uses the corresponding formula for the closeness-like centrality to compute the centralities of v_s. To verify the efficiency of the algorithm in the parallel case, we evaluate the speedup factor of the algorithm by running on a cluster which starts from a single machine and goes up to 6 machines. And the speedup factor is defined as follows, where Ts is the algorithm running time on a single machine, and Tpm is the running time on the cluster of M machines. From the figure on the right, we can see that the proposed parallel algorithm has a good speedup factor when the cluster increases. So, we'll continue to do related experiments by using Bordex database, which including the social network and the information about personal and companies. And after data cleaning, we have a summary of the financial social network in 3 regions, like Table 1, where network density is defined as the ratio of the actual number of edges to the maximum number of edges in the network. Besides, we also generated 3 random networks based on random graph, WS Small World Network, and BA Scale Free Model, respectively. We compare closeness centrality, K-closeness centrality, and K-harmonic centrality on real-world social networks and randomly generated networks. In each network, 10,000 vertices are randomly selected to compute centrality, where K is set to the values 2, 3, and 4. And we use Spearman's rank correlation coefficient to measure the correlation between closeness centrality and other centrality. We can see that both K-closeness centrality and K-harmonic centrality are significantly associated with closeness centrality. When K equals 4, the correlation of both approximations to closeness centrality reaches 1 for all experiments we performed. And Table 3 shows the variance statistical analysis details of North America. We can see that 3-harmonic centrality has a higher coefficient of variation, lower kurtosis, highest interquartile range, and higher overall range in the real-world networks. It is significantly correlated to the closeness centrality. Therefore, the 3-harmonic centrality is an appropriate substitute for closeness centrality when performing a similar financial social network analysis. Besides, we computed the average computing time of real-world networks in the 6 machines. We can see from the figure 3, the computing time of 3-harmonic centrality is about 40% of closeness centrality. On the other hand, we have cleaned the Bordex database from the first beginning. And for the employment information of individuals, we get the current executives for each company, including CEO, CFO, COO, CMO, CTO and CIO. Then, we calculate the centrality of this social financial network, which composed of multiple executives. We use a variety of centrality algorithms, including our proposed 2 approximate measures, to analyze the relationship between executives' social connections and company values. Taking the CMO as an example, we can find from Table 4 that although the correlations vary across regions, They suggest that the social connections of company executives have a significant impact on a company's market capitalization. As we can see from the table, the correlation reaches over 0.31 for North America. In Europe, the correlation is higher, and it reaches over 0.56 for triangle counting. Besides, we also summarize the correlation between the three harmonic centrality of executives and market capitalization and revenue in tab. 5 to compare different executives. And we can see that the social relationship of the CEO is an excellent choice to predict the company's market capitalization and revenue in North America. While in UK and Europe, CTO or CIO is the better choice. At last, let's summarize the content from this paper. We expands the existing network centralities and proposes two novel centralities to facilitate network analysis on social networks. K closeness centrality based on closeness centrality, and K harmonic centrality based on harmonic centrality. And we design the parallel algorithms which are designed based on the pre-gel model show a good speedup factor when the size of the cluster increases. Then we take them to experiments to verify the feasibility and scalability of parallel algorithms and find that the approximate measures simplify the computation while maintaining a high correlation with closeness centrality. So, this is my presentation for this paper. Thank you for listening.